We're going to start with a very easy example to talk about forces or Newton's laws. We have 3 laws that we're going to talk about. So I'm going to assume that we have a skater who's pushing a mass that has 100 kilogram, that mass is 100 kilogram, across a sheet of ice that's horizontal plane, and it's frictionless. We're going to ignore friction for now. He applies a force, F, which is 50 newtons, in the I direction. If the box starts at rest, so it starts from rest, what is the speed V after being pushed for distance equal to 10 meters? What to do? He wants, what is the strategy? How can we actually target that problem? He's asking us to find displacement along, he wants to find us, to give us, he is asking us to find the speed after it moves for 10 meters. So that means that we have to use the kinematic equations. We have to use kinematic equations. So I'm going to say that he's asking for a speed. I'm going to write down the 3 kinematic equation. V equal to V initial plus AT. X equal to X initial plus V initial T plus 1/2 AT squared. And the last one, that's V squared equal to V initial squared plus 2A delta X. We have to use one of those equations to get the velocity after it moves a distance 10 meters. Which one should we use? If I choose the first one, I will need the initial velocity, the time, and the acceleration, assuming that it starts from 0. So I will need 3 quantities. If I use the second one to get the velocity, I need acceleration and time. And I don't have both of them. All what I have, I know is the distance. If I use the third one, then I will need V initial, A, and delta X. And if we look at the givens, we'll find that we have only delta X and V initial. But we don't have any time. So I will not use that one because it has the time and I don't have the time. I will not use that one because also it has the time and we will need to get the time. But I might use that one if I know what is the acceleration. So we need the acceleration. All what we need is the acceleration. Then plug in the values in here, we'll get V. How can we calculate the acceleration? That's when Newton's second law becomes a useful tool actually. Force equal mass times acceleration. So force equals to mass times the acceleration. The force, that's 5 newtons, equal mass, that's 100 kilogram, 50 newtons, equal to 100 kilogram times the acceleration, which means that the acceleration will equal to 0.5 meter per second squared. Now, if we know the acceleration, we can simply plug in the acceleration here, putting delta x to be 10 meters, and V initial, because it starts from rest, equal to 0, then we can find the V, and that problem is solved. Okay, guys? So that's how to solve that problem. We got the acceleration by force equal mass times acceleration, then we got the acceleration, then we substituted in that equation by the acceleration and x minus x0, which is delta x equal to 10 meters, then we got the velocity. Excuse me? What should we put in for delta x? What should we put for delta x? Yeah. That's 10 meters. 50? 10 meters. 10 best? Yes. Delta after being pushed for a distance equal to 10 meters, we need the velocity after it moves at 10 meters. 10 minus 0? 10 minus 0. Good. And we get the answer. Answer is 3.2 meters per second. Okay. Saying that, guys, I want you to pay extra attention to that equation here. That's not a equation, that's just a problem that we're going to solve together in class. We have a mass m1, and we push it with a force equal F, and that results in an acceleration equal to A1. Then we get another mass that has a mass of m2 Nagy. Focus. We have a mass m2, and we push it with the same force F, but we find out that the acceleration now it's twice of A1. Now I'm going to stick the two of them together, and I'll push them with the same force. Can you guess what will be that acceleration as a function of A1? I'll say that problem again. I push the first mass with a force equal to F1, and we find out that that object will move with an acceleration A1. Then I move another object with the same force, and it will move with an acceleration equal to twice of A1. Now I'm going to stick them together. I'm going to put the two objects together, and I will push them with the same exact force. Can we guess the acceleration? C, D, معي؟ B, مريم. C, Nagy. D, so can you get us, I forgot your name. Guys, Nagy, forgot your name. Shinawi is saying, well, that depends on the relation between the two masses. We have to find out the relation between M1 and M2 in order to get that. And my reply to that, can you guys find the relation between M1 and M2 from the givens? M1 is twice of M2. I forgot your name. Abdurrahim. Abdurrahim is saying, well, M1 has to be twice of M2. That's why if you apply the same force of them on them, the second M2 will move with twice the acceleration of A1. That means that M2 is half of M1. That's a good answer. That's a good strategy. Yes.
We can say that both will be 3 over 2.
So, I forgot your name again. Hassan is saying, now, if we know that M2 is half of M1, then M1 and M2 is 1.5 of M, and M is M1, which is 3 over 2. And mass and acceleration are inversely proportional. Then, and Hassan is saying that mass and acceleration are inversely proportional. If the force is constant, then you get 2 over 3. So the answer is A. That's what Hassan said. Farida, then we'll go to Nada.
What do you mean reverse proportional?
Hassan is saying, he's claiming, I don't know if this is correct or not. I'm just saying what do you guys say out loud, so it can be recorded. Hassan is saying, if the force is constant, then you increase the mass, you decrease, the acceleration get decreased. If the force is constant, if you increase the mass, the acceleration gets decreased. And he's saying that in a different way. He's saying that mass and acceleration are inversely proportional if the force is constant. Which is the case, the force is constant. But is his claim is valid or not? I don't know. You tell me.
You can just do it mathematically.
Do you agree with Hassan? Do you all agree with Hassan? It makes sense. It makes sense. If I push Mahmoud with a force F, he will move with an acceleration of 1 meter per second. But if I push Ali, which is a little bit heavier than Mahmoud, then he will move with less acceleration. You increase the mass, you decrease the acceleration if the force is constant. Okay, that's one good thing. Sharif, so what are we supposed to do now? How can we solve that?
We can, the way Hassan said is right, or we can just take one quantity be to be constant, and with it,
Which is the force?
okay, but also the mass, for example, you know that M1 is double M,
And as Abdurrahim said, that M1 is double of M2 because of the relation of the acceleration that's given to us.
exactly, so M1 plus M2
Mhm.
will be 3 M2.
3 of M2.
Exactly, so it will have 1/3 of the acceleration of M2.
Mhm.
That means that 1/3 times 2 is 2 over 3, which is 8.
Okay. Okay, so I'm going to repeat that again on the slide. And Nagy is going to, I made a mistake in here, and Nagy will spot out that mistake and he will tell us where is the mistake. Okay, Nagy? So focus. I said, I go straight to the problem. I need to find the acceleration when we stick them together. That's what I usually do. So I said that if we apply a force F on the two masses, then the acceleration in that case is going to be the force F divided by the two masses. Now my problem now is not just to get the acceleration now. My problem is to find the relation between M1 and M2, and if I do that, I can easily find what is the acceleration A. And this is the statement that Abdurrahim said. Since A2 is double of A1, that means that M2 is half of M1. Then, that means that M1 plus M2 is 3 over 2 of M1, 1.5 of M1. So I'm going to put that in the equation. The acceleration A, that one, is 2 over 3 times F divided by M1, which is F divided by 3 over 2 M1. That's the equation. Okay guys, done? The remaining part is to find the relation between A1 and A. We know that F divided by M1, that's A1. So I'm going to replace F by M1 divided by M1. I'm going to replace it by A1, then you get the answer. The answer is A is 2 over 3 F1.
طب دكتور لو انتوا ما عملناش substitution بارقام خلاص يعني نقول مثلا M1 equal 4 و M2 equal 2
Because this is a more general way. And when you solve a problem for a specific case, some people might think that this is only valid for those numbers. But this is more general. Okay? And if you do computer programming for that, you cannot assume numbers. You have to use general way, then you ask the user to plug any numbers, you get the answer, he gets the answer. Okay? Forces. So we're going to consider, guys, two kinds of forces, a contact force, a non-contact force. A contact force and action at a distance force, non-contact force. If I push Mahmoud, that's a contact force. If I stand on the ground, then my weight on the ground, that's a contact force. The force between Earth and that marker, that's a non-contact force. There's force between them. That's why if I let go of that marker, it's going to fall to the ground because it's going to be attracted by the gravitational force. But there is a force between them. Guys, someone has something that beeps. Okay. So there is a non-contact force between them. If I take you a little bit off the subject and we talk to electricity, if we go and to electricity and magnetism, if you remember it from high school, if you have two charges, there will be an electrostatic force between them, right? And we call that non-contact force. If you have two charges, they might repel or attract each other depending on the type of the charge, but we call that non-contact force. So I'm going to give you examples here for contact and non-contact forces. If I push on the desk, that's a contact force. If the ground push on your chair, that's a contact force. If a spring push or pull on an object, that's also a contact force. Action at a distance or non-contact force, example for that is gravity, gravitational force, and electrostatic force, which is electricity. Let's look at the forces acting on you right now as a student in this class. You're sitting on a chair. Actually, I changed that. So this is the forces acting on you. Can you guys look at the forces acting on you? This is my thumb on your head. This is the force from the thumb on the head down. And of course, your head is going to be pushing on my thumb back, upward. And this is satisfy Newton's third law. So that's how we read it. The force from the thumb on the head. The force from B on A. Equals the force from A on B. A negative sign.
How?
Wow, what?
Doesn't it go down? That means that it's not equal.
How come? You're now sitting on that chair, and I'm saying that the force you put on the ground is equal to the force the ground pushes back on you. And if my statement is not correct, if you push on the ground by a force more than the force the ground pushes back on you, you're going to sink inside the ground. And if the ground pushes back on you by a force more than the force you push on the ground, you're going to fly up. Okay? So if I squeeze your head, then means that I'm putting forces on you that's just more than the force your head can stand. But your head still be pushing on my thumb on the opposite direction with the same equal forces. This is more examples, guys. Those are more examples for contact forces. I'm not. You can just read through them, but one of them is collision of two moving objects, pillion poles, for example. That's a good example also for contact forces. Gravity, this is an action at a distance, the force between planets. This is a non-contact force. Gravitational force. If you have an object, on Earth, that's us, Ali, for example, and I want to calculate what is the forces from Earth on Ali, magnitude and direction. There is a gravitational force that states that if you have two objects, whatever those two objects are, M1 and M2, there will be a force between them all the time. That force equals to a constant G, the force, gravitational force between any two objects will equal to G, a constant G, and I will give you the value for that constant in a minute, times mass of the first object times the mass of the second object divided by the distance between them squared. This is the gravitational force between any two objects. So I'm going to apply that now on the forces from Earth on Nagy. I'm going to apply that formula now to calculate the forces between Nagy and Earth. So the force now is going to be Fg will equal to gravitational constant G, which is just a constant, regardless of its numerical value, times the mass of the first object, that's mass of the Earth, divided by the mass of Nagy, times the mass of Nagy, divided by the distance between Nagy and Earth. What is that distance? It's measured from the center of Earth till the center of Nagy. So it's going to be R Earth, radius of Earth, plus half of the height of Nagy. Square. Right? If we look at those numbers, Nagy, half of his height is only 1 meter at most. The radius of Earth, that's hundreds of kilometers. So it's much, much higher than that h/2. So I can safely ignore that height from the surface of the Earth to the object. I can ignore that. I can consider that the distance between any object on Earth and Earth, it's just the radius of the Earth square. If you look at those quantities, G multiplied by the mass of the Earth divided by the radius of the Earth, those are just constants. The numbers are in the book. Do not memorize them. If we need them, they will be in the formula sheet. But if you look at them and you plug in the numbers, you'll find those will equal to 9.8. And this is our famous acceleration due to gravity, G. And we can say that the gravitational force now between Earth and any object on Earth equal to mass times G.
That's good.
Yes. And that's where mass times G came from that gravitational force between any two objects. And this is valid between any two objects. Okay, guys? So, here is the value for G, the radius and the mass of the Earth. Actually, they are knowns, they are given. But more important is if you have two objects, Ali and Mahmoud, there will be a non-contact force between them. And that force, that's the gravitational force. The force from 1 on 2, from Ali on Mahmoud, should equal to the force from Mahmoud on Ali, but opposite in direction. So that means that the force that Earth is attracting Nagy by equals to the force Nagy is attracting the Earth by. That's an attractive force between the two objects. But the reason that Nagy, if you let go of Nagy, he will fall down to the Earth, and Earth will not fly to Nagy, the difference in masses. One of them has a very small mass compared to the other one. So one of them, the smaller the mass, the greater the acceleration. One of them will move with high acceleration, that's Nagy. The other one will move with a very, very tiny acceleration that we will not even notice because of the difference in masses.
So if the 6 billion units is a word stood in one country, the rest was it?
Say that again.
If the 6 billion units stood in one country, the Earth was it?
If the mass is comparable to the Earth, then this will push that with the same mass, and nothing is going to happen. Equal forces.
It's greater, we're going to fall to the ground.
Say that again.
So like all 6 billion people.
Yeah.
So mass is greater than the mass of the Earth.
Yeah.
The Earth is going to fall.
The Earth is going to be attracted to them. It's going to hit them.
So if we jump, the Earth goes up.
Yeah.
Oh.
So this is a good example for a gravity problem. You have a student who has a mass of 55 kilograms. What is the gravitational force on that student? That's easy. That's mass times G. So it's 55 kilograms. That's the mass of the student times 9.8, and we get 539 newtons. Okay. I want to skip that one. I will skip that part. And I will also, we talked about Newton's third law, guys. So I'm going to skip that part. But I want to look at this. Assume that I'm standing on the wall like this. That's exactly what you see. Can we identify all the forces on the object? Guys, I want you to identify all the forces on me. I'm going to be standing like that. That's what you see. And I want to identify all the forces on me. I don't care about the forces on the wall or the floor. I want to identify only the forces on me. Any ideas? Yes.
The wall on pressure, the ground on pressure, and
Thank you. I forgot your name. Muhammad is saying that it's the wall is going to be pushing back on you. The floor is going to be pushing up on you, and the gravity, earth, is going to be pushing you down. Those are the three forces. Yes, Sharif.
But isn't the force that the ground is pushing you exactly the same as the gravity?
Assume that you have in class a small aeroplane that flies. There is a gravitational force between that aeroplane and gravity and earth. Yes, that's mg. And assume that it gets closer to earth. Will mg change? No. It will change a little bit if you actually get into it, if you be more accurate, but it's going to stay mg. If it stands on earth, will mg change? But what? Are we going to get a new force? Yes, since they are touching each other, the airplane and earth. The earth is going to be pushing back by a force regardless of the magnitude of that force. I don't want to get into that now on the aeroplane. So on the aeroplane you have two forces, mg down and the force from the ground pushing back on the aeroplane up. And that's exactly what Muhammad said.
Okay, they're there, but they cancel each other. You're not moving, so your net forces are here.
Yeah, I agree with that.
So I guess there's a force that you.
And I did not ask you to calculate the forces. I asked you to identify the forces on me. Okay, so guys, those are the three forces that we're talking about. And actually, the force from the ground on me will equal to the force from me on the ground. And the force from the wall on me is going to be the force from me equal to the force on me on the ground, but in the opposite direction. Example of bad thinking. Can you read this and tell me? I'm telling you, this is sometimes I think that way. And this is a good way to talk about bad thinking. Read the problem and tell me where did I go wrong. Bishoy? I'm saying that I'm saying what Sharif just told us a minute ago. If I'm pushing, if I'm standing, I'm pushing on that block, and this is ice, so there is no friction. If I'm pushing on this, and there is no friction, and the force from the block on me, from the mass on me, equal to the force from me on the mass, how come this moves? I'll say it again. One more time. I'm going to assume that we are on ice. And I'm going to be just, guys, standing and actually not pushing, just leaning on that chair. And of course, there is ice, that chair will move. And my thinking tells me that this is really weird. How come? If I push on that chair by a force F, and the chair will push back on me with a force F. So the net force is 0. How come the chair moves? It shouldn't move if the net force is 0. In my statement here, I made a mistake. In my thinking, I made a mistake. That's why I say that this is a good example for bad thinking. I want you guys to identify that mistake.
I will return, I will go backwards, I will not. So when it goes like this, I will go like this.
Okay?
There is no need for force because there is no friction.
There's no need for force. I didn't say that.
Force, once I got activated, I won't stop the boat. So there's no friction.
But that's has nothing to do with what I'm saying. I'm saying why the net force equal to 0? Why isn't the net force equal to 0? I'm now pushing on this, and that moves. If it moves, that there is an acceleration. But at the same time, I'm saying that the force from me on the chair equals the force from the chair on me. So the net force, as Sharif said a minute ago, equal to 0. So nothing should move. Farida? Yeah, they are different masses, but even if they are equal masses.
I know, but I don't know, maybe I know that the forces are the same.
Yeah. Okay, Muhammad first.
These forces are equal. There's also equal force on block on ice and ice on block.
Yeah.
X-axis.
Yeah. On x-axis, on y-axis.
And the x-axis is going this way. That's why
No. There is no force from the ice on the block that way. It's only that way. It's vertical.
no, it's also
There is no friction. There is no friction. That's why I choose ice. Sharif.
So the block is put on ice, so if we take a step and look at the net, like the forces acting on the block,
Mm-hmm.
in case when I'm leaving, I
Mhm.
see a net force in this way, since there's no force acting on the object in the opposite direction to hold it.
Yeah. That's the way to think about it. Sharif said, now you're talking about a system, and the system is you and the block, and the net force on that system is 0. But if you talk about the block only, the force on the block, not from the block, is the force from you on the block. That's why you will have an acceleration on the block. But if you talk about the two of you, then the net force on the two of you, on that system, you and the block, is going to be 0. And if you look at it, if you move that way, if the block moves that way, you should be moving in the other direction. Someone said that. In such a way that, that's what we're going to talk about in chapter 9, the center of mass of the whole of the two things is not going to change, as if they did not move. So since we're talking only about the block, and I'm asked about the acceleration on the block, so I have to consider only the forces on that object, not the forces from the object. We're trying to find the acceleration of that object, right? So I have to consider only the forces on the object. The forces on the object, not the forces from the object. And if you look at the forces on the object, it's not 0. The forces on the object, it's not 0. It's something. That PM. Okay? Okay, now if I put a wall behind that block, let's identify the forces in here. We have a force from the man on the block, and you have a force from the block on the man on the opposite direction. You have the force from the block on the wall, and you have the force from the wall on the block. Okay, this is the problem that I was talking to you about, guys. Now I have an object A, an object B, and they are like what you see right now. I want to identify how many pair of forces are present in this system. So some of you said 1, which is not even here. Some said 2, some said 3, some said 4, and some said 5, which is also not here. But I can discuss the 5 as well.
17.
So who said 5?
I said so.
Ali said 5. Okay, Ali, can you identify them?
Here?
No, the 5. You're 5.
Well, in a very abstract way, since if you're standing on top of the chair, then there's a gravitational force
Mhm.
from the earth on you
Mhm.
and on the chair,
Mhm.
and there's the action force, contact force on each four.
Right, like,
Like,
yeah. Okay, and in here, what's you gonna have? What are you gonna have? Ali.
4.
4. Why 4?
Or 3, sorry.
Why 3?
There's a contact force between A and B.
That's one pair. A on B and B on A. That's one pair.
Contact force between B and the ground.
What's 1 and 2? That's 2 pairs.
Yes, and gravity from A and B to B.
Gravity from B and Earth.
A to A.
And A, that's 4.
I'm sorry.
That's 4. There's no gravity. Oh, because they are in contact. Because they are in contact. There's no gravity between them because that distance is very, very small, so you can ignore that. But if you want to count it, that's okay. Okay, then it can be 5. If you want to count it, that's good. I will answer that again. I'll forget it now. Okay, well, Nada, what did you say? Can you actually answer that for us? Can you actually identify how many pair of forces do we have? 3. Why 3? From A to B. From A pushing back on pushing on B, and B is pushing back on A. That's one pair. From B to the ground, B is pushing on the ground, and the ground is pushing on B. That's 2 pairs. And gravitational force between A and the ground and Earth. Actually, let's not say the ground, on Earth and of course then the opposite one. How about the gravitational force between B and the ground? No, we'll go back to the airplane example or the bird example that I told you. Okay, I forgot your name. Mahmoud is saying, actually, we can be a little bit more accurate and say that there will be also gravitational force between A and B. It's going to be very, very small because the distance between them is very small, but there will be a gravitational force between them. Yes, it can be.
So it will be 5.
Yeah, it can be if we count that one, but usually we do not count that one if the distance. For example, the force between you and Ali now, right now, as a gravitational force, that's very, very, very small that we do not even count it. And if you know if that force is really present right now, it is present. But if it's significant, you will go and get attracted to your colleague all the time. Okay? So that's why we do not really count it. Okay? But that was a good example in here. So I'm counting them again one more time. Gravitational force between A and the ground, that's 1 pair. Gravitational force between B and the ground, that's 2 pairs. Contact force between A and B, that's 3 pairs. Contact force between B and the ground, that's 4 pairs. Okay, and this is a summary of what we have studied so far. Newton's 3 laws. First law that says that an object is subject to no external force. If there is no external force acting on any object, that object, that's you right now, will stay at rest or it will move with a constant velocity if we look at it from an inertial reference frame. For any object, some of the forces will equal to mass times acceleration. Third one, forces always occur in pairs. You can never find a single force. All forces always occur in pairs. And the force from A on B equals the negative of the force from B on A. Okay? If you push on the wall will push back on you.
The law which states that every action has a force.
Yes. That's Newton's third law. If you hit someone, he will hit you back. That's what I would say. No. No, say that again. Second law is totally different than the third law. So say what you want to say again. Say it again.
So if every action has a reaction,
Mhm.
in the second law, the net force will have
The net force will have. Yeah, but remember, we'll go back to the bad thinking. We're thinking about the force on the object. And when we talk about forces in pairs, we talk about forces not only on me, but on me and the wall. So if you're talking about, if I push that one, what are the pair of forces do we have? Forget contact between the chair and the ground and me and the ground. It's the force from me on the chair and from the chair on me. Those pair of forces. When this move with an acceleration, then I have to consider only the forces on the object. Okay? Okay, so that's the end of today's lectures. Guys, you still have like 5 minutes, so ask anything you want to ask about. Yes, Muhammad.
Because you're thinking, you only think about the object.
Guys, listen. Yes.
You're thinking, you only thinking about the object.
When we try to find the acceleration of that object or the forces acting on the object, I have to consider only the forces. Sit down. Sit down. The forces on the object. That's it.
Say, so there's gravity on you and you on the gravity.
Mhm.
Whereas if we're looking at just you, is you just the gravity on you, why are you not going on?
Oh, the gravity on me is an attractive force. The gravity on me, that's an attractive force. It's not a repulsive force. The force from the gravity from Earth on me, it's attracting me, not pushing me up. It's one thing. So look, if I let go of this, it's going to be attracted to Earth. So it moves up, it moves down. So this is very important that the force from Earth on that object, this is an attractive force, not a repulsive force. So attracts the object to the center of the Earth. The same way that object attracts Earth to its center. Okay? Farida?
So if there's no gravity, there will be no force. If there's no gravity, there will be no.
If there is no gravitational force, now then I will only force that I will have is the contact force between me and the ground.
And why will you have contact force?
Now if you're saying that if there is no gravity, we will not touch the ground. Yeah, but if we touch the ground, there will be a contact force between us. If we touch it.
We will not be able to, we will not push, even if you touch the ground, we will not push the zero force.
But there will be a force. If if I put my hand right there, there is no gravity along that direction. Am I putting a force on the wall? Yeah. So if I stand on the ground and if I do this, if I push on the ground like this, then I'm doing force on the ground and the ground is pushing back on me by the same force. Nada? If I just touch you, as long as I'm touching it, there is a force between us. Okay? But if I don't touch it, I just put my hand right there, and the distance between them is 1 millimeter, then I'm not touching. There is no force between them. Gravitational along that direction.
No gravitation force between your hand and the force.
Yeah, that's okay. Yeah.
If there is no gravitational force, there will be no A, so F equal M times 0 means 0, so it helps the force. There's no force. There's no contact force.
No, if you... okay. Am I touching the wall?
Yes.
Yes. Is there any force between me and the wall?
Yes.
Yes. Even if I barely touch it, without really pushing, forget this. Forget my hand because you might think that's heavy. Is there any force between the paper and the wall? Yes. Is that a significant force? Is that a huge force? No. But do we have a force between the paper and the wall? Yes. Of course, there is no contact force between them. Now there is no contact force between them. Only that force between them, which is very, very small for it. What else? Sharif.
How do you
Okay, Sharif, then we'll go back to you.
Okay, again to the introduction where you said about the plane,
Mhm.
that even in the material flying, it has the FG, which is the gravitational force between it and the center of gravity.
Yeah.
But in this case, it's the air that's pushing it up.
Okay, this the air that's pushing it up.
The
Yeah, there's another force between them that actually the thrust of the air. Correctly. That's correct.
Okay, so in that case, there's only one pair of forces acting on the plane.
No.
Air and gravity.
Yeah, and I did not want to complicate things by telling you or the force in the plane, so I have to give you a simple, very simple example though. Yeah.
Something very simple,
Yeah.
which is the gravitational force, Fg,
Mhm.
and the force the air is applying on the wings, so that the
Yeah.
plane to
And yes,
so that's one pair.
there's two pairs. MG, earth and airplane and air and airplane.
But in that case, how should the plane stay at the same position? In that case,
It will not stay because it's going to be attracted. If you shut the engine off, it will fall down because it's going to be attracted by the gravitational force to the earth.
that means that the lift of the air
Mhm.
is twice the
No, it's exactly, you have to, if you want to just stay at that level, all what you have to do is just put the engine on to produce some air down, exactly equal to mg. So you're going to stay at that. You're going to stay put at that. But if you put more force down, then you go up.
okay. So when it's on the ground,
Guys, don't listen to us. This is very, very philosophical, but that's fine. So do not get confused by it. That's good.
so when it's on the ground,
Uh-huh.
there is the force of mg, that's become the force
Yes.
on the ground, and then there's another mg between the plane and the earth,
Mhm.
right? So again, the ground will be pushing up the.
Are you American diploma, RG, ثانوية عامة, Canadian? American diploma. It's okay, I'm sorry. It's almost the same, but it's the same kind of education. Here in Egypt or somewhere else? Okay. So, I know. We studied the same thing from maybe fourth grade till now, but it's every time we studied, it's by new, little bit with a higher level. So I know that you studied all that before.
Yeah, I understand.
Yeah. So, okay, ask again. That's fine. Say, Ali,
Regarding this,
yes, you can leave.
Because we never considered like, okay, if my hand is on the left,
Mhm.
well, in theory, there's infinite number of forces acting on it.
Count them.
Okay, the force between my hand and the sun, the force between my hand.
Oh yeah.
Okay, but there's an infinite number.
Yeah.
Okay, so
Not infinite, but many of them. If you consider all the objects around you.
exactly.
Yeah. If you will say that we have a few billion people on Earth, then we're going to count all the pair of forces between me and those few billion. Yeah.
What do we consider? Like, okay, the FG between this binder and the center of the Earth is FG.
MG.
MG.
Yes.
Okay, but at the same time, the force, if I put it on the ground, between the contact force between the ground and it is
Okay.
MG both ways.
Good. Because I didn't really want to get into what are we going to take next, but let's look at this. Give it to Hani again.